So in this class, there's really three big themes. And we've now finished the first one, which is the advanced techniques in integration. All right, so this one, we're done. We now move on to our second one, which is now that we can actually use this tool in more general cases, what are some more things we can do with this tool? Because so far, if you were to ask, well, what's integration for? Most people will say, well, we can find an area, but is there anything else you can do? Turns out there's a lot you can do. So we're going to spend the next several weeks talking about applications of integration. And so it says here, it says, you are a sum, every question involves a sum. And that really is what's going to happen. That's going to be our common theme of applications of integration. Now, the last part of the course, which we get to look forward to, we start that after spring break, is sequences and series. And that's fantastic. It's a lovely topic. So what's our approach to applications? Now, let's first off understand what integration is for. Integration is built to answer one particular type of question. Now, it's a very flexible question, but the question it's built to answer is, what is the total? Or you could say it as, how much is there? That's what integration is about. Now, a lot of questions can be phrased in this way. So, what's the total area? That's a question that we're very familiar with. But we can do other geometrical things. What's the total volume? What's the total surface area of a three-dimensional shape? What's the total length of a curve? But it doesn't have to be just geometrical. We can go into physics. What's the total mass? Where's your center of mass? We'll be dealing with those types of questions as well. You can go into finance. What's the total money? People care about that. There's lots of things that you can phrase in this way. Now, the way we solve these problems all boils down to the same basic approach. We take what we're looking for, what our total is, and we're going to break it into small parts. Now, why do we break things into small parts? It comes back to sort of the philosophy that we saw in Calc 1, where we might have this line that's wiggling around quite a lot. It's not very well, doesn't have a nice single behavior. But when we zoom in, that line becomes very flat and we understand it. Well, the same ideas apply here. It's like, well, we might have something which is varying quite a bit. But when we break into a small part, that small part acts pretty well. It's a well-behaved part. And therefore, when I break things into a small part, the second point, I can get a good approximation for that part. I won't be perfect, but it'll be good. And now I'm going to add all these approximations together, and lo and behold, that gives me the answer. Now, of course, how do you do better? Well, the answer is you break into smaller parts. And you go smaller and smaller. Now, whenever you hear words like smaller and smaller, or closer and closer, that really means there's a limit process involved. We're going to hide all that in the background, so you won't see limits showing up. So here's what we have. Our total, what we're after, we add up. So remember, that's what this sigma means. Sigma for S for sum. Everything's about adding up. Our value of our function times our delta xi. And what delta xi represents will vary depending upon what we're doing. And we'll see that it has different interpretations. And so as we get smaller and smaller, our sum becomes what we call an integral. So this is the definite integral. And you see that this f of xi becomes f of x, and our little delta xi becomes dx. So let's start with what we know. So we're going to be working in the next couple of sessions here. We're going to be focusing on geometric applications. So we'll start with one that's very familiar with all of us, which is area. So this is not a big idea. This is just to help us sort of get ourselves into the right mindset. So when we're after finding the area of something, we say, all right, suppose I want to find the area. I have these two curves. There's this f of x curve, and there's this g of x curve. And I want to find the area, the shaded area that's in between the two curves. Well, what we do is we think about breaking things into little slices. So here's a little tiny slice. And I can say, well, how much area is in that slice? It's fxi minus g of xi. That's the height, times the delta xi, which is the width. So the f of xi minus g of xi, the height. The delta xi is that little tiny length across. That's the area of one piece. We add them all together, and we get the total. And of course, in the limit becomes the integral from a to b of f of x minus g of x dx. Now, one of the things that I hope you start getting to the practice of is not memorizing formulas like f of x minus g of x dx, but rather thinking about what they represent. So for instance here, f of x minus g of x, I can think of this as you're integrating a height, and the dx is your width. And if you can get into this sort of mindset about what things are, you'll find that you can be a lot more flexible in new situations. So if we modify the problem slightly, it'll be easy. Whereas if you're very rigid and you only memorize formulas, such as fx minus g of x, it becomes very hard. So, on to something new. Let's do volume. Now, how do we think of volume? So, first off, I should say it's very hard to think of volume when you can't draw pictures very well. Someday, when the math department can finally afford to buy all its paper clips, we'll set our sights on getting a 3D printer, and then we can print something 3D. But hopefully you can sort of get a vague sense of what we have going on here. So this is a shape. It's supposed to represent a three-dimensional shape. It's kind of a strange shape. The base is a half circle. And then what's happening is there's various slices here. There's this ridge that runs through. And as you slice it, you get these triangle shapes. Now, what's our idea? Well, our idea is we're going to take our shape, and we have these small slices. Now, here I should make it a little bit thicker, so let's go ahead and add some thickness. And when we take one of these slices, we can say, all right, what's the volume of this slice? Because my goal here is I want to figure out what the total volume is, so I'm going to find the volume of one slice. So I look at this and say, well, I can think of it as there's a little bit of a thickness. That's my delta x, I. And the subscript for I here is just sort of an indexing subscript. You can just call it delta x if you want. All right, so how do you get the volume? Well, what you do is you find the area of this shape. So the area, A of xi, that's the area of the cross-section. So once we take the area times the height, well, area times height is volume. So that says I get the volume, this little piece here, A of xi times delta xi, that's the volume of a slice. And then, of course, in the limit, that becomes the volume. The integral from a to b, a of x dx, a of x, this is our, again, area of a cross-section. And the dx, it's not just there for show. You know, we keep saying, notation's important, notation's important. Because the dx isn't just there for, you know, it likes to hang out. No, the dx means something. So the dx has a physical meaning, and this is the width. So width times area, or if you like, height times area. So let's try a problem. Find the volume of the shape lying over the region x squared less than or equal to y less than or equal to 1, where the cross-sections perpendicular to the x-axis are equilateral triangles with one side on the plane. Now, if you're trying to visualize what could that possibly look like, it's not too far off from what this picture is doing right here. But we'll go into it and try to reconstruct it from the description here. So let's figure this out. First off, we have a region, so let's focus on this region. X squared less than or equal to y less than or equal to 1. Let's see what that looks like. So here, we can really think of this as a pair of inequalities. X squared less than or equal to y, y less than or equal to 1. Now y less than or equal to 1, that's easy. You come up to this curve y equals 1, and you're everything below there. This you can think of as y greater than or equal to x squared. So you have this curve x squared, and you're greater than or equal to that, so you're everything above. So when you put these two together, what do we get? Well, it's part of the parabola, but only up to the top. So here's the y equals 1, here's y equals x squared. So this is our region. So that's a two-dimensional thing, but we're after a three-dimensional picture. So I have my region, and now we're taking cross-sections, slices, and we're going to be perpendicular to the x-axis. So perpendicular to the x-axis, so here's the x-axis, which means I'm slicing this way. So I'm perpendicular. But it's not just a two-dimensional thing, it's really a three-dimensional thing. So there's this whole slice going on, up and down. So let's maybe draw this in a nice three-dimensional way. So I'm going to take this, and I'm going to lay it down in three dimensions. So here we go. So that when we slice, the slice that we had before is still a slice, but now it's we're up in three dimensions. And what do we look like? Well, what does it say? The cross sections perpendicular to the x-axis are equilateral triangles with one side on the plane. So here, this is the plane. So I have one side of my equilateral triangle is there, and then I'm coming up. So as I move across different cross sections, what I'm going to get is I'm going to get different triangles. So that's what's happening. And again, this should be very familiar. It's very much like what you see happening in this picture, where we're getting different cross sections, our triangles, as we move across. Dun, 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 dun. Okay. What does it look like? I don't know. Roughly something. It's hard to figure these out sometimes, but that's okay. We don't have to have a perfect picture. We just have to have a vague understanding. Okay, so what do we need? Well, we go back to our basic formula, which is good because we've only learned one formula, so it's easy to figure out which one to use. Once we've learned two formulas, it'll be twice as hard. All right, so volume, integral a to b of a of x dx. All right, so what do I need to figure out? Well, what I need to figure out are certain things such as what are a and b? Well, okay, that's not so bad. Where do I start and stop with regard to x? Negative 1 and positive 1, because that's where x squared is equal to 1. And now, I should point out here that we are integrating with respect to x here because our cross-sections vary as we change x. It might be that we have it so that the cross-sections vary as you change y, in which case you integrate with respect to y. So there's nothing sacred about the symbol x. You adapt it for whatever you need to do. Okay, so that's good. We can integrate negative 1 to 1. The dx will be dx. That's not so hard. So the last thing to figure out is the area of x. Now the area is built off of what's happening in our cross sections. And we know our cross sections are equilateral triangles. So what we should figure out is what's the area of an equilateral triangle. Let's just make some notes down here. So let's suppose that L is the side length of one of my equilateral triangles. Now, if I want to know the area of a triangle, what's our basic formula for area of a triangle? Yeah, 1/2 base height. Now, you might say, hey, that's easy, because look, isn't that side also L? Yeah, it's equilateral. That means all three sides have the same length. But that doesn't mean that the height is L. What we need to figure out is this length. But it turns out there's a nice fact if you were to look at some pieces here. So for instance, this part here is half the length. It's half the side. And now, what do I have? Well, I have two lengths inside a right triangle. And so you can solve for the other side. So what is this length? Does anybody know? I'll give you a hint. It involves an L, but there's something else. There's a square root of 3. Anything else? It's not quarters. Square root of 3 over 2. And if that sounds familiar, like, well, that's kind of like something we see in trig functions, it's because it's something you see in trig functions. So this is a 30, 60, 90 triangle, just scaled up by a factor of L. All right, so what's the area? Well, the area would be 1/2 base, so L, times height. Square root of 3 over 2 times L, which gives us square root of 3 over 4 times L squared. Now, you might say, okay, that's what goes there, right? Not quite. What's wrong? Yeah, this is L. What do we want to have here? Something involving x. All right. But certainly, it is true that we'll have the square root of 3 over 4, something squared. So the last thing for us to do is figure out what is the L. So for that, we say, okay, according to our basic idea, our L is the base of our equilateral triangle. And according to the rule, we put the base right here. So this length is our L. It's how far we are between the top curve and the bottom curve, because that's the base. So you come over to our picture here. See, that is the one side of our triangle, which coincides with that. So what's that distance? Well, it's the distance between 1 and x squared. And so what we put inside here is 1 minus x squared. All right, that's the hard part. I have to figure out, okay, what's the right length for one side of my triangle? And it's going to vary. Because if you come over to the edge, your triangle is very tiny. In the middle, it's much bigger. So you have to remember, it's varying with L. Now from here, it's just integration. The hard part is setting the problem up. And that's going to be the theme for the next couple of weeks. Very rarely are we going to have a very challenging integral. Most of the challenge is going to come in setting up the integral. So you want to get comfortable with setting things up. So in some sense, you could say the first part of the course, we got really good at actually doing integrals. This second part of the course, on which we're currently embarking, we're going to get good at setting integrals up to do. So to integrate this, 1 minus x squared squared, well, you'd square it. And then you can just integrate each piece individually. Now, one thing you could do if you wanted to is instead of going from -1 to +1, you could go from 0 to 1 and double. Why could you do that? Well, there's symmetry, right? The shape is the same on both the left half and the right half. You could also say symmetry because what you're integrating is an even function. But we'll go ahead and say from -1 to +1. You'll get the same answer. You just have to put in twice as much work. So x minus 2/3 x cubed plus 1/5 x to the 5th from -1 to +1. Now I'm regretting not doing the symmetry, but all right. Square root of 3 over 4. 1 minus 2/3 plus 1/5. Subtract -1 minus 2/3 times -1 plus 1/5 times -1. Well, you can clean that up a little bit. Let's work on this one. Common denominator of 15ths. So you get 15 15ths minus 10 15ths plus 3/15. You put that together, and you end up with something 15ths. No, it's 8/15. It's not just something. This is going to be minus 8/15. I'm just really fast at that. No, symmetry, right? Okay, so you get 8/15 minus 8/15, which means that this is 16/15 times square root of 3 over 4. Well, if you take 16 divided by 4, you end up with 4 root 3 over 15 once you simplify. All right? This last step was basically multiply square root of 3 over 4 by 16 over 15. Okay, well, let's do another one. Find the volume of intersection of two cylinders of radius 1. Now, where the intersection is a right angle through the center of the cylinders. So, if you can try to visualize, we have a cylinder running in one direction and a perpendicular cylinder, and they cross. And the question is, how much volume do they have in common, that shape where they intersect? Now, it's not so obvious what that shape is. So we have to sort of think about it. Now, one of the things you could do is, if you look down the various cylinders here, so if you look through this red cylinder, what you would see is you'd actually see a circle. If you look through the blue cylinder, you'd see a circle. And if you look from above, what would you see? You see a square. What square would you see? Well, I probably should use a color that shows up on red. You would see that square. That's what you'd see if you looked from above, because that's what's common. So it's kind of an unusual shape. Now, one of the things that we have to decide, and this is a more subtle problem, is we know we only have one tool, so we're going to use our tool. And our tool is, let's figure out what cross-sections look like, and let's add them up. The question is, how do we take cross-sections? Because that's not so clear. Because there's a couple of different directions you can go. And depending upon which direction you can go, you'll get a slightly different setup. So we're going to do cross-sections in the following way. So if we think about this, say, in 3 dimensions, you might think of x, y, and z. We're going to go in the z direction. So we're going to go, our cross-sections are going to go up and down. We're going to try to understand what they look like. So, what's happening? Well, let's think about just a normal cylinder. And again, we're going to take our cross-sections going up and down. So if I'm at a particular height, then my cross-section will just be a line. So I'm just looking at one cylinder right now. So that's what a cross-section would look like, just a line. When I translate that into the picture, this line becomes a thin segment. And it's going to be in both. So what happens is that my cross-sections are actually squares going up and down. Does that make sense? I'm sorry. This is one that you have to think about for a while. But as I vary the height along that z direction, the different shapes I'm forming are squares. Okay. Now that's good news for us, because what's the area of a square? Yes, length times width is length squared, right? Okay, so here we go. We're going to say that the volume is the integral of area, I'll call it z, because I'm going to think about moving up and down in the z direction, a to b. Now, we know a couple of things. We know these have radius 1, so we can think of this as going from -1 to +1. So if I'm thinking about my picture here, so -1 to +1. My dz is still fine. That's still dz. And the area, well, this is going to be a square. So I compute the area of a square by squaring something. So what I need to figure out is what is the right choice. What goes into that piece? Well, okay. So we come to our picture, which, as I look at it, might be a little bit too small for our purposes. So we're going to embiggen it. So here's our embiggened circle. Positive 1 upstairs, negative 1 downstairs. And we have our little piece across. Now, what are we after? Well, we're after how long it is across, because that's this length in the picture. If we know that length, then we square it, and that's the area. So, we're thinking of z as varying, so I can think of this part as being z. What else do we know about this circle? Radius is 1. So we can put a 1 in a lot of places. You might say, well, you already did that. See, that's 1. But there's other things that are 1. For instance, this is 1. And now, lo and behold, we have a right triangle. So what's the length of this half? It's the square root of 1 minus z squared. Pythagorean theorem strikes again. It's a good tool. You should know it. Now that's halfway across, all the way across. If we wanted to go all the way, how far would it be? Yeah, times it by 2, because there's symmetry. So we get that this is a square. The length of each side is 2 square root 1 minus z squared. So that's what goes here. 2 square root 1 minus z squared, quantity squared. All right. Now, we don't have to worry about the picture anymore. Now it's an integral. We have to solve this integral. I think we can. I'm pretty optimistic about our chances because, well, let's actually use symmetry here. So instead of going from negative 1 to positive 1, we'll double and go from 0 to 1. So we'll put a little 2 here, showing that we double. If we square 2, that'll become 4, and then 1 minus z squared. Well, 2 times 4 is really 8. So we have 8. Then we have the integral here would be z minus 1/3 z cubed. And evaluate from 0 to 1. If you plug in 0, you get 0, which is nice. That's one of the reasons we like to hang out with 0. It just makes everything 0. All right. How about 1? Well, you get 1 minus 1/3. 1 minus 1/3, also known as 2/3, times it by 8, gets us 16/3. And that's the answer. It's kind of a cool answer because if you think about the problem, whenever we see circles, what do you tend to expect? You tend to expect pi. But no pi was harmed in the solution to this problem. It turns out to be a rational number, 16/3. All right. Well, let's double our number of formulas. And we're going to learn a nice thing. So we're going to talk about volumes of revolution. And it's still a volume, but what we're going to focus on is a very particular type of volume. Namely, we start with a region in the plane, and then we spin the region around a line. Usually we'll use an axis, but it doesn't have to be an axis. We're just spinning our shape around a line. And so what happens? Well, we're going to use the same process as before. We're going to take our shape and we're going to break it into small little pieces. And our pieces, in particular our cross sections, what happens is that they're circles. You see, we can see that up here in the picture. We took this little piece, very small piece here, and we spun it. And when we spun it, because the way we formed our shape is by spinning, what we formed was a circle. Now, if you add a little bit of thickness to it, it becomes a disc. So some people call this the disc method. So, all right. So what do we get? Well, the volume is the integral from a to b of pi r of x squared dx, where r of x is the radius. So what's happening is that this piece here is simply area. So it's the same formula we just had. We're just saying here's a nice special case where the area turns out to be a circle. So the same process as we had before. And again, it's nice to not just memorize the formula pi times f of x squared dx, but say, okay, f of x represents something. And in this scenario, f of x is now representing a height, but it really represents a radius. What's our radius? If you can understand that, it's much easier to change depending upon what your situation is. So let's do an example. Find the volume of the shape formed by rotating the region 0 less than or equal to x less than or equal to pi, and 0 less than or equal to y less than or equal to 2 sine x around the x-axis. So the picture here is we have this curve. 2 sine x would look a lot like the sine curve, but it's twice as tall because of the 2. And the sine curve is positive between 0 and pi, and so our region is that region there. Now, go ahead and shade it in. Something like that. Okay. So we're going to take that region, and we're going to spin it around the x-axis. And I also like to mark where we're spinning around just for reference. So there's where we're spinning around. So what do? Well, even though we've just learned one technique, I think it's good to get in the habit of just sort of reminding ourselves what we're doing. I always like to think to myself, all right, when I'm finding a volume, I think about making a little slice and what happens to it. So here's my little slice. I'm going to spin that around. And as I spin that around, I see, aha, I'm forming what I call a disk. So this is the disk method. So that just helps confirm. We'll see, this foreshadows there might be another method. Well, come back next time, right? More to do, more to do. So we still have more to do today. I'm just saying that. There's other options. So what do we have? So volume will be integral. A to b it will be what? 0 to pi, which we get from our bounds, which weren't marked here, but we can throw them in. 0 to pi. And then we get pi. And then we get our r of x. The r of x is the height. All right, so what is our r of x here? 2 sine of x. Then we square at dx. Okay, so how do you integrate something like 2 sine of x quantity squared? What can you do? So if we clean up a little bit, this would be the same as 4 pi sine squared of x. So you're faced with the integral of sine squared of x. 4 pi is a constant. Constants don't need to worry about. What do you do for sine squared? Power reduction. Good. Good. You still remember. It's nice to remember things. Okay. So this becomes 0 to pi. Do you remember what sine squared of x becomes? 1 minus cosine 2x over 2. Now the 2 goes into the 4 pi, so we can write that as 2 pi Integral of 1, well, that's x. Integral of cosine 2x. There's a half, and the half will be because of that 2 on the inside. What's the function? Sine. Now, do I need to change this minus sign to a plus, or is it correct as a minus? It is correct as it is. Yeah, because the integral of cosine is sine. It's always, you got to be a little bit paranoid because it's just so tricky, those cosines and sines. It's almost like they're trying to throw us off. All right, so we plug in pi. We get pi, and then there's a half sine of 2 pi. Sine of 2 pi? 0. So we end up with 2 pi times pi. That's 2 pi squared. We plug in 0. 0 minus half sine of 0. And sine of 0 is still 0, which means our answer is 2 pi squared. All right. Okay, let's try another one. Find the volume of the shape formed by rotating the region 1 less than or equal to x less than or equal to e cubed and log x less than or equal to y less than or equal to 3 around the line x equals 1. Well, all right. First thing to do, draw a picture. And it's not so bad. Let's see. We have x equals 1. I'll just put a little dashed line here. We'll say this is 1. We have x equals e cubed. I don't know exactly where it is. We'll say that's over here. There's e cubed. Log of x. Y equals log of x. Let's think about that. What is the value of natural log at x equals 1? Natural log of 1? 0. Okay, so it starts at 0. Natural log of e cubed? Oh, it's 3. That's kind of a nice value. So it's going to go up here. 3. And log comes up. So it's coming up, doing something. And okay, something like that, right? It doesn't have to be totally exact, just a rough picture. All right, and let's see, what do we know? We know y goes from the log of x up to 3. Okay, so we're coming in between these. And we're going from 1 up to e cubed. So our region is that sort of, kind of almost a triangle, but it's not a triangle because one of the sides is curved. And we're rotating around the line x equals 1. Which means we're going to rotate this way. The round line x equals 1. So when we end up with the shape, I should have planned better, but it will be some sort of shape where that looks something like that. Well, question is, what do we do? What do we do? Well, we only have a couple of methods. Really, it's just one method, which is to find the area of a slice. So, what's different here? Well, one big difference is our perspective. Where should we be integrating with respect to? Well, the reason I'm asking what we should be integrating with respect to is because that'll help us solve the problem. So, no. Okay, somebody said y. Yes. It is the y variable. That's the correct thing. Because we should really think of what's happening is that if we take a slice, instead of a vertical slice, to take a horizontal slice, when we spin that horizontal slice around, that's when we're getting our circle. So we're going to think about horizontal slices. Now, does that change our formula? The answer is no. It's still the same philosophy. The x is just a placeholder. Okay, so we think about what we need. Our basic formula says volume. It's the integral a to b. There's a pi, and then radius squared, and then there's a thickness, which you can think of that as a height, if you like. And we just think of our things. We're integrating with respect to y, so our thickness is a small change in y, so that becomes a dy. Now we need to think of our radius. So let's think about this curve for a second. This is the curve y equals natural log of x. Is there another way to write y equals natural log of x? In particular, I'm interested in x equals something. E to the y. And where is that coming from? Well, natural log and exponential are inverses of each other. So if I say y equals natural log of x, that's the same as saying x equals e to the y. So I say, okay, well, how is that helping me, that piece of information? Well, that's helping me because what I really want to know is I want to know a radius, which is a distance. And so the radius is the distance between the point where I'm rotating and the furthest point out. So how far apart are these two? Well, it depends on my y value. Down at the bottom, very short. At the top, in fact, we can say exactly what it is. It's e cubed minus 1. Partway in between, well, what will be our radius? E to the y minus 1. It's that distance between. So e to the y minus 1. What will our bounds be? Where do we start in terms of y? Start at 0, and we go up to 3. So integral from 0 to 3 pi e to the y minus 1 quantity squared dy. And now from here, not really many surprises. So I do have one more idea. So I'll walk through it really quickly. Whenever you have something squared, usually the best thing to do is just to square it. So you multiply it out. Then each part is something which is easy to do, at least relatively speaking. So the integral of e to the 2y, that's 1/2 e to the 2y, then minus 2 e to the y plus y. And you evaluate from 0 to 3. And if you plug in 3, you get pi 1/2 e to the 6 minus 2 e to the 3 plus 3. Good. Are we done? No. What haven't we done? Yeah. We so often, when we plug in 0, we think, oh, it's just going to be 0. But you got to check. What happens here when you plug in 0? Well, e to the 0 is 1, not 0. So 1/2 minus 2. The y is 0. All right. And you could leave your answer like that, or you can say, oh, I have a plus 3. And then here you can combine these together. This is really a minus 1/2. Plus another minus makes a plus 1/2. So you have 3 plus 1/2, that's 4.5 or 9/2, I think. So if you wanted to, you could combine those together. 1/2 e to the 6 minus 2e cubed plus 9/2. And there we go. Now, the last idea. It's actually fairly simple, which is to say, what if there's a hole? So, in other words, before, when we spun things around, it was a solid circle. But what if it's a circle with a smaller circle punched out? Now, this was called a washer. And if you've ever built anything, you'd often have to have a washer as part of your set. All right. So the question is, how do you do volumes by washers? Well, the answer is you think of the shape, the area of the cross-section. It's a big circle minus a little circle. So the way you do that is you say, all right, I'm going to take the area of the big circle, so that's pi big radius squared, and I'm going to subtract the small circle, pi little radius squared. And then that's my total area. So again, it's just the area of the cross-section times your little thickness. So it's the same philosophy It's just saying here's a very specialized case that when you have a certain volume that you form by spinning, and your cross sections become big circles minus little circles. So we'll just quickly go through this last example. Y equals x squared and y equals 2x. If you graph those, you get y equals x squared and you get y equals 2x. They actually intersect. Can you see where they intersect at? They intersect at 2. So if we were to spin this around the x-axis, what we have is, if we're spinning around here, we have our pi integral 0 to 2, so the pi being from there. The top curve is 2x, the bottom curve is x squared. So it would be 2x squared minus x squared squared dx. So that would be if we spun it around the x-axis. But there's a quick question. What happens if we don't spin it around the x-axis? We spin it around this line. First question, is that legal to spin it around that line? Absolutely. You can spin it around any line. Okay, so what changes? Well, the thickness, does that change? Yeah. No. Do our bounds change? No. Because we're still going to the same x values. What changes is our radii. These are the part that's changed. So what happens? We get pi integral 0 to 2. Now the question is, how far are you from this curve to where you rotate? It's no longer 2x, it's what? 2x plus 1. Or if you like, 2x minus minus 1. And now the inner radius, it's not just from the x squared down to the axis, it's x squared down to here. So what's that radius? Yeah, x squared minus minus 1, x squared plus 1 squared. And that would be what would change if we spun it around another line. And that's it for now. Come back next time and we'll do some more. Have a good day.